Everyone. Welcome to the 11th live problem solving session for the course on concrete technology. I'm Sethi Vinayagam, a PhD scholar in the civil engineering department at IIT Madras. Okay, so let's start with an overview of the lectures covered in week 11. Okay, so we had 4 lectures, and in week 11 we continued with the durability aspects, right? So in particular, we started off our discussion continuing on the corrosion that we ended with week 10. So in that lecture 34, we looked at corrosion potential and corrosion kinetics, right? So how this corrosion occurs in the rebars, right? So the mechanism and also the kinetics, which determine the rate of this corrosion reactions. And then we also looked at what are the different effects of corrosion and also some preventive measures that we can take to prevent the rebar corrosion. And in lecture 35, we will look at different models on service life related to the corrosion and the durability, the general strategies for for having a durable concrete structure. And in lecture 36, we looked at we moved into the special concretes, right? So we so moving away from OPC and other things. So we looked at some special concrete. So in particular, we were looking at high strength concrete, right? So special concrete means designed for specific application. So one particular type of them is the high strength concrete. So we looked at some historical perspectives and also then what is the role of porosity, pores, and other micro features in that determine the strength of the concrete, and other factors like water to cement ratio, the aggregate and properties of other materials. So in so what is their role in developing high strength concrete. And in lecture 37, we again continued with the properties of these high strength concretes, and then we moved into talk about other types of other special types of concrete. And finally, an introduction to the self-compacting concrete was given, which will be continued in the week 12. Okay, so with that, we'll now move on to some problems related to these concepts. So the first problem or question is, during the design life, with the age of permeability of concrete, so what happens to the concrete's permeability with age? So the options are increases, it decreases, it remains the same, or it first increases and then decreases. Okay, the poll is launched. Okay, we have one vote for option B, decreases. So the right answer is also option B, it decreases, right? So we are talking about the permeability of concrete. So it has to do with, how easily, the fluid flows through it, right? So that has to do with what is the porosity, right? So if you have higher porosity, and also not just porosity, but also how interconnected the pores are, right? So that will govern your permeability. Right, so here we are talking about what happens to permeability when the age of concrete increases, right? So during the design life. So with age, so what happens? Hydration occurs, right? So we know that hydration is a continuous process. So as hydration occurs, what happens, this hydration products are formed. So you will have the porosity reducing with age, and therefore you will see that the permeability also reduces, right? So therefore the right option is that it decreases with the age of the concrete. Okay, question number 2 is, which of the following does not govern the corrosion propagation period? So the options are loss of steel cross section, compressive strength of concrete, delamination of rebar, and cracking of the cover concrete. Okay, so we have one vote for option B, compressive strength. Okay. So the right answer is also option B. It is the compressive strength of concrete, which does not govern the corrosion propagation period. Right. So here we are talking about the corrosion of the rebar, right? So that corrosion propagation is governed by, so loss of steel cross section, it happens, right? So the diameter of the steel rebar, so that will reduce as corrosion propagates. There will be delamination of rebar. So delamination is the the removal of, or the the erosion of the protective covering that is provided on the surface of the rebars, and cracking of cover concrete, right? So as the corrosion propagates with time, so because of the stress development around the concrete, around the rebar surface, we'll see that because of that cracking initiates there, and then it so all the cover concrete, so the cover concrete is that which is placed above the rebar surface till the surface of the concrete, right? So that portion, again, we'll see cracks over there with progression of the corrosion. So all A, B, C, A, D, A, C, and D are actually happens during the corrosion propagation. It's only B, the compressive strength, which is not a factor in the, which governs how corrosion propagates, right? So therefore, B is the right option. Okay, question number 3 is, controlling the water to cement ratio and curing are effective in reducing the segmentation of pores in concrete. So you should say whether the statement is true or false. We have one vote for option A. Okay, so the right answer is option A. It is true. Right. So here we are saying asking whether the water to cement ratio and curing, whether controlling these factor has an effect on the segmentation of pores. Right. So what is the segmentation? Okay. So let if we have a piece of concrete, right? So it will have some pores, right? So there'll be pores at different locations. Okay. So what we are talking about here is the segmentation of pores. So it is about the separation. Segmentation means it is about having separate the pores being separate from each other, not really interconnected, right? So suppose if we have more pores, there is higher chance that you will have the pores, the joining together, right? So the pores may join together, and then you'll have larger pores, and it will be easier when the when they are interconnected. So it will be easier for external factors to get into it, and then for corrosion or other degradation process to occur, right? So here what we are saying is if we control the water to cement ratio and also do good curing, so is it effective in reducing the segmentation? So it is true, because by controlling the water to cement ratio and by controlling the curing, so we have a control over the porosity, right? So how many pores or how large the pores are, right? So because we are able to reduce the porosity, so there is a better chance that the pores will be also not connected together. So when you have more number of pores, it is they will also be interconnected. So there is a higher chance or a good chance of them being interconnected. So when you have reduced the porosity, so there is a good chance of segmenting, right? So separating them, right? So therefore these two factors are effective in controlling this segmentation, right? So therefore the right option is A, it is true. Okay, question number 4 is adding silica fume in concrete should be done in optimal quantity. If added in excess above 15%, they will reduce the porosity by their secondary reaction. So is the statement true or false? Okay, any answers? Okay, we have one vote for option A. Any other answers? Okay, we'll look at the answer now. So the right option is A, it is true. Okay, so what are we talking about? It's about adding silica fumes and their effect on porosity, right? So as you know, with silica fumes are finer than your cementitious material. They are cementitious material because they have some cementitious properties, and they are much finer than your cement, right? So what happens is they will occupy the pores that is created by larger particles, right? So we know that the pores that is created by your coarse aggregate will be filled with your fine aggregate, and the pores that is created by them will be occupied by the cement and cement gel and so on. Right. So here, because silica fumes are much finer, so they will occupy all the finer pores. Right. So if you add more and more of these quantities, so it will occupy those finer pores, and then they will help in reducing the porosity. Right. So this is one of the reason why you will get better strength, because they will help in providing better packing, right? So in addition to their cementitious property, they will also help you in reducing the porosity, right? So therefore, this given statement is true. Okay, so question 5 is cement undergoes hardening upon loading. So we have to say whether the statement is true or false. Okay, I have launched a poll.
Hello, sir. Good evening, sir.
Yeah, good evening.
Sir, what about the exam pattern for the next week, sir? The
So exam pattern, it will be available from the portal, so you can check that.
portal itself, it shows only the pen and paper exam or online mode or offline mode only that is available, sir. But other questions are come. It may be the 1 mark or 2 mark.
Okay, so for
That
that
will
you
be
can write
considered in
to
the.
NPTEL support. They will be able to help you out with that.
If you give any format
Uh,
based on we will prepare it, sir, for easiest.
okay,
Suppose the
I am
other
not
questions
involved with
are.
that. The paper setting and all. So I'm just helping with this problem solving session. So it will be better if you write to NPTEL. They'll be able to help you out with that.
Okay, okay. That mail ID ko email you will write it, na?
Sorry.
The common queries are asked by the common individual. You will ask that question in online forum, sir, regarding the question paper pattern.
Yeah. So I think it will be online. So you can write to NPTEL. They will help you with that.
Online is okay, sir. Online okay, but
Mm-hmm.
I think last time I wrote so many examinations.
Mm-hmm.
So the slot may be the forenoon session or afternoon session, whatever it may be. So
Mm-hmm.
in that before that, suppose if the 50 questions, each question carries 2 marks, so that is out of 100. But in some examinations, there are some linked questions are also available. So because
Okay.
of this 12 program, really need to spend more much of time in respect to the like in our if suppose we take the agri technology books course. So in that we have the mixed designs like IS, AC and DOE method.
Mm-hmm.
We will focus on only those or otherwise all the weeks is going to equal importance for all the units.
Yeah, I think it will be there will be equal importance for all the units. So, but regarding anything with respect to exam, it is better you write your questions to NPTEL. They will able to clear all your doubts.
Okay.
Yeah.
Yeah. Okay. Thank you.
Yeah. Okay, so we have one vote for option A, true. Any other answers? Okay, so let's take a look at the answer now. So the right option is, it is B, false, right? So we are talking about the hardening process. So it is not dependent upon the loading condition, right? So whether you apply or load, it does not affect whether or how your concrete is going to harden, right? So loading is not going to help you harden it. So it is the hydration process which governs the hardening and not the load application, right? So therefore the right option is false. Okay, question number 6 is, which of the following is not a property of the self-compacting concrete? So the options are flowing ability, high viscosity, segregation resistance, and vibration eliminated.
Sir, and sir, this is Durga, sir, and I have one more doubt, sir.
Okay, yeah, go ahead.
Uh, that is, sir, all the content, if you refer all this, whatever the slides put it in this particular concrete technology book,
Hmm.
those are enough for the examination, or otherwise, we will going to refer like the standard textbooks called MS Shetty, and some other textbooks are also available, sir, like some of the standard textbooks.
I think the given material should be fine. For if you need any detailed explanations for that, you can refer to the book. But the concepts or the concepts that were taught in the lectures, I think that will be enough.
Okay, okay.
Okay, any answers? Okay, we have one vote for option B. Any other answers? Okay, so let's take a look at the answer. So the right answer is option B. It is high viscosity, right? So here we are talking about self-compacting concrete, and the question is, which of the following is not a property of the self-compacting concrete? So as the name suggests, so by self-compacting, so what do we mean? We don't need external compaction, right? So once we place it, so we don't have to do any supply any external vibration or compaction to the concrete. So that is the whole idea of self-compacting concrete, right? So because of that, so as it is self-compacting, you don't need to do any external compaction, so vibration is eliminated, right? So D is actually a property of the self-compacting concrete, right? So then how it is achieved, because it has high flow value, right? So it is highly flowable, therefore that is why you don't need external vibration for it to to spread uniformly, right? So because of that only vibration is eliminated. So flowability is also a property of the self-compacting concrete. And C, segregation resistance. So because it has good flowability, it should not uh, in that process it should not segregate, right? The components that make up the concrete, so the different ones should not should stay together. So all the different components, it should not segregate or separate into individual components, right? So therefore it should still remain homogeneous. So segregation resistance is also a property that we require in the self-compacting concrete. But high viscosity is the only one which is not a property of self-compacting, because when you have high viscosity, you will not have actually high flowability, right? So actually A and B are opposites, right? So therefore, when you have high flowability, you will not have high viscosity, and that is the right option. High viscosity is not a property for self-compacting concrete, right? So therefore, the right option is B, high viscosity. Question 7 is, to make high strength concrete, the water to cement ratio has to be lowered. So this will lead to a loss in workability. So to overcome this, which of the following methods can be adopted? So the options are add super plasticizer, increase the water content, increase the cementitious content. Option D is decrease the cementitious content. Okay, so this is a multiple answer question. So more than one option may be correct. So you can answer accordingly. We have one vote for options A and C. Okay, any other answers? Okay, so let's take a look at the answer. So the right options are both A and C, adding super plasticizer and also increasing the cementitious content. Okay, so why are they correct? So what are we talking about? So here we want to make high strength concrete, and for that, water to cement ratio has to be lower, right? So one of the requirement is that we need a lower water to cement ratio. So but this will lead to loss in workability. So how do we keep the water to cement ratio low, and but also combat this lowering in the workability? So what can we do? So one is adding super plasticizer. So as we have already seen in the lectures of chemical admixture. So the super plasticizer or the water reducing agent, so they help in increasing the workability while keeping the water content same, right? So by not adding more water, by keeping the water content to be same, if you add more super plasticizer, you will get more workability, right? So therefore you need not, so for the given water to cement ratio, you can increase the workability by adding super plasticizer, right? So this is one valid option. So the other one, B says to increase the water content. So this is not appropriate. Why? Because we need to keep the water to cement ratio lower. If you increase the water content, what will happen is your water to cement ratio will increase, right? So even though your workability will also improve, but it is not correct because our strength will reduce by increasing the water to cement ratio, right? So therefore we cannot increase the water content. C is to increase the cementitious content. So this also can be done because by increasing the cementitious content, what will happen? Your water to cement ratio will go down, right? So therefore, this is also appropriate method. And D is just the opposite, decreasing the cementitious content. So this will actually increase your water to cement ratio, right? So that is not required here. So therefore, the right options out of the four are both option A and option C. Okay, so moving on to question number 8 is the electrode potential at cathode is dash than electrode potential at the anode. Okay, the poll is launched. Okay, we have one vote for B and one for C. Okay, any other answers? Okay, so let's take a look at the answer now. So the right option is option B. It will be more. So the potential at the cathode will be more than the electrode potential at the anode. Right, so we saw in the lecture for taking an example of corrosion of iron, right? So how the cathode and the anode in the metal, so they'll be in the same metal. So a region will be acting as a cathode, and the another region will be acting as the anode. And we are looking at the potential at the anode and also at the cathode, so between the metal as well as the electrolyte. And we showed that At the cathode, at the cathode, which is shown on the right side here, the potential active potential will be higher than the potential at the anode, right? So this is the anodic region between both the metals as well as metal as well as electrolyte, and the cathodic region between the metal and the electrolyte. So at the cathodic region, the potential will be higher than at the anode, right? So the right option is that B, it will be more. Okay, question number 9 is, what are some of the factors that can prevent or delay the rebar corrosion? So the options are the quality of the cover concrete, the use of blended cement, use of waterproofing coating, and all the above. We have one vote for option D. Any other answers? Okay, we'll take a look at the answer now. So the right option is option D, all of the above. Right, so here what do we want to do? We want to prevent or delay the rebar corrosion, right? So what are the some of the strategies or methods that we can adopt to do that? So one is having a good quality cover concrete, right? So cover concrete is, as I said earlier, it is the layer between the surface of the concrete to the outer layer of your rebar, right? So we have a good cover concrete, good quality cover concrete. Then what happens? Your ingress of chlorides and other chemicals and also moisture will be prevented, right? So it will be lesser, and therefore the rebar corrosion can be delayed. So if it is happening at a slower rate, it can be delayed. If it is not penetrating, then it will be also prevented, right? So because we know that it is the wet corrosion which affects your rebars, right? So therefore this preventing the ingress of these chemicals and moisture is necessary. So a good quality cover concrete will help us do that, right? So therefore A is right strategy. The use of blended cement. So again, blended cement will help you in reducing the porosity, right? So we are talking about using mineral admixtures, right? So that's what we use in the blended cement. So that will, as we saw earlier, how it reduces the porosity, right? So therefore your porosity will come down, therefore your permeability will also be improved. Therefore, it will also help you in preventing corrosion. Third is the use of a waterproof coating. So this is also a measure. So as we said, so we want to prevent the ingress. So providing a coating on the top on the surface. So a waterproof coating will again help us in preventing the moisture from entering the concrete, right? So therefore, that will also help us in reducing or preventing or delaying the rebar corrosion, right? So all the three strategies given here are perfectly valid. Therefore, the right option is D, all of the above. Okay, question number 10 is which of the following is used as a qualitative measure of durability? So the options are the compressive strength, crack density, permeability, and porosity. Okay, we have one vote for option C. Okay, any other answers? Okay, we take care of the answer now. So the right option is C. It is permeability, right? So when you are talking about durability, so how did we define durability? It is, the ability of the concrete to, perform its intended function, right? And therefore, so the durability. So it is about being able to resist the degradation from external factors, right? So how do we measure that? So one of the qualitative measure is the permeability, right? So because this degradation is occurring because of the external factors, so and we saw in many of the different attacks, so they require the presence of moisture and also chemicals for entering the system. So permeability is one measure, so that will that is the directly related to measuring this ingress, right? So therefore, permeability is one way in which we can quantify how durable the system is, right? So if you have higher permeability, which means that it is easier for the degradation process to occur, right? So the deterioration can happen faster. So that is one way in which we can measure it, right? So therefore, permeability is the right option. Okay, question number 11 is interconnected pores lead to options are high permeability, low permeability. It doesn't affect the permeability and porosity of the concrete is reduced. Okay, we have one more for option A. Okay, any other answers? Okay, let's take a look at the answer. So right option is option A. It is high permeability. Right, so here we are talking about interconnected pores, right? So I already mentioned that permeability and the porosity are related, right? So also it's not just the volume of the pores, but also how connected, how well connected they are. So when you have well connected pores, what happens here? Uh, there will be more flow, right? So that it will be easier for flow to occur, right? So therefore, which means that the permeability of the system will be higher, right? So because of this interconnected pores, right? So and we also looked at how the rate of flow varies as a function of your permeability or how it governs uh, your permeability, right? So it is so when you have a given rate of flow, so it depends on your gradient, hydraulic gradient, and so it is proportional to your gradient, and the constant of the proportionality is your permeability, right? So when you have interconnected pores, then it will affect your permeability, and it will be higher because of higher flow that will take place. Okay, so question number 12 is, as per IS 456-2000, high strength concrete has a compressive strength in MPa between which of these ranges? So the options are 40 to 60 MPa, 60 to 80 MPa, 80 to 100 MPa, and greater than 100 MPa. Any answers? We have one more for option B, 60 to 80. Any other answers? Okay, let's take a look at the answer now. The right option is option B. It is 60 to 80 MPa, right? So here we are talking about the highest standard. So as per highest standard, so when you have any engineered concrete, so the normal strength concrete is generally in the range of 40 to 60. Right? So this is for the normal one. So if you have 60 plus in the range of 60 to 80, then as per the highest standard, so it is so this is at the 28 days. So the compressive strength at the 28-day strength, if it is between 60 to 80, then it is called the high strength concrete, right? If you have anything greater than 120, so in that case it will be very high strength concrete, right? So therefore, according to the Indian standard, it is between 60 to 80. That is the range given for the high strength concrete. Okay, so the right option is B. So question 13 is aggregates with lower MSA is preferred over higher MSA for developing high strength concrete. So is this statement true or false? Okay, we have one vote for option A. It is true. Any other answers? Okay, we'll take a look at the answer. Right, so the given statement is actually true. Right? So why? So here we are talking about high strength concretes, and for high strength concrete, we are saying whether we have to use lower MSA or higher MSA. So what is MSA? It is the maximum size of the aggregate. So higher MSA means it is the coarse aggregate, right? So CA. So when you look at high strength concrete, so you'll see that generally the percentage of the coarse aggregate will be lower, right? So the size that we use, or the maximum size that we use will be lower, and also the content of the coarse aggregate will be generally lower, and the fine aggregate content will be higher, right? So that helps us in developing the high strength concrete. So the given statement is true, but why do we do that? Is because we looked at in the lecture. So what is the effect of the aggregate size? And when you have aggregates, what happens is that there will be stress concentration that will be occurring at the interface between the aggregates and the gel, right? So we looked at this in the normal strength concrete, so where it fails. So we have the aggregates. So we looked at three different phases. One is the aggregate, then the gel, and also then the ITZ, the interstitial transition zone, right? So it is the cracks will be propagating through that, because that is the weaker area, right? So because in that area there will be stress concentration occurring. So when you have a larger size particle, so when you have higher MSA, what happens is that the region where this stress concentration is occurring, so that will be in a larger volume, because you have a larger aggregate size. So it will occupy a larger volume, and the region around that larger aggregate, there will be higher stress concentration, and therefore it will reduce the strength. So whenever we are going for high strength concrete, because we want to lower the stress concentration, we will try to reduce our the maximum aggregate size that we are using. Right? So therefore, that is the reason why the given statement is true, that we prefer lower MSA over higher MSA when we are developing high strength concrete. Okay, so therefore, the right option is A. Okay, question 14 is densified with small particles concrete DSP is used in which of the following applications? So options are flooring, safe nuclear entrapment, overlay on existing concrete. Option D is all of the above. Yeah, Durga, do you have a question? If you have a question, you can unmute yourself and ask, or you can make use of the chat box. Okay, we have one vote for option D, all the above. Any other answer? Yeah. Okay, so you have two votes for option D. Okay, the right option is option D. It is all the above, right? So we are looking at one of the special concrete. So we looked at different special concrete. So one of them is densified with small particles concrete (DSP). Right? So and therefore it can be used on all these different applications for flooring, nuclear entrapment, overlay on existing concrete. So for flooring, because this concrete has a better resistance to abrasion, right? So therefore it is suitable for flooring applications. Nuclear entrapment, because this is densified with small particles, so therefore it has uh, it will the penetration through this concrete will be much difficult, so therefore it is perfect for for entrapping nuclear wastes. And overlay on existing concrete, again for existing concrete may have cracks and so on. So overlaying with this densified concrete, so it will help us in extending the life of that existing structure by protecting those any ingress through those existing cracks, right? So therefore it is suitable for all the three applications. So the right option is D, all of the above. Okay, so question number 15, it's a numerical problem. So RCC exposed to atmospheric environment exhibited 10 mm depth of carbonation after 4 years. What is the likely carbonation depth after 25 years? So the options are 19 mm, 25 mm, 62.5 mm and 100 mm. Any answers? Yeah, yeah. So the PPTs are also shared online. So in the portal itself, the link, it's all the PPTs are shared in a Drive folder. So the link to the Drive folder is given in the portal. So if you open the live interaction link in the portal on the left hand side, so you'll see the channel link as well as the Drive link. So all the PPTs are uploaded in that Drive folder. You can access it from there. Okay, we have one vote for option B, 25 mm. Okay, any other answers? No, both are there actually. Let me share the link. Give me 1 minute. Okay, I have shared the drive link in the chat. So in this drive folder, you'll see all the uh, presentations that were used in the session so far. So this will be updated with this week's content and the next week as well in the same folder. Okay, so any other answers other than B? Okay, so let's take a look at the answer now. Okay, so right option is B, it will be 25 mm. Okay, so that is the right option, and now we'll take a look at how it is obtained. Okay, what is the question? It is about carbonation depth. Okay, so here we are given one situation where after 4 years of exposure, like there was carbonation occurred till a depth of 10 mm. The question is what will be the likely depth after 25 years of exposure? Okay, so how do we solve this? So we saw a similar example last time, right? So what is the relationship between the carbonation depth and the time of exposure? So we know that the carbonation depth x is proportional to the root of the time it is exposed, right? So if t is your time of exposure, then x is proportional to square root of t, and therefore x is equal to some constant k times the square root of t, right? So this is the relationship between carbonation depth and your time of exposure. And now what are we given with? So we are told that after 4 years, the carbonation depth is 10 mm, right? So we are given with for one particular time period, right? So 10 mm, it is 10 mm, the depth. So is equal to some k times square root of 4, right? So this is one of the situation, right? So from here we will be able to find out what is this constant that is relating this x and t. So root of 4 is 2, so therefore k will be 5. Okay, so we find out what is the value of the constant. So using this, we will be able to find out for the second case. So second case is what is the carbonation depth after 25 years. So how do we do that? So we know the value of k. So now we need to find what the value of x is after 25 years. So k is 5, so k will remain the same, so that will not change. But now the exposure is for a longer period, which is 25 years. So which is 5 times, so root 25 is again 5, so which will be then 25 mm. Okay, so after 25 years, we expect that the carbonation depth will reach up to 25 mm, right? So therefore, the right option is B, it is 25 mm. Okay, any questions? Okay, so we use this relationship that we know between the carbonation depth and the time of exposure, and for one, so and the constant is the only unknown in that equation for us. So using one known depth after a particular time, so we found out what that constant is, and using that for another given time, which is 25 years. Okay, so we found it to be 25 mm. Okay, so moving on, question number 16. Nernst equation in the context of rebar corrosion is used to estimate which of the following. The options are the equilibrium potential, the rate of corrosion, resistivity of concrete, and none of the above. Here we have one option as A. Any other answers? Okay, two options for A. Alright, so let's take a look at the answer. So the right option is option A. It is for determining the equilibrium potential, right? So when did we look at the Nernst equation? So it was when we were discussing about the potential or the corrosion potential, right? So the rate of corrosion, it depends on the the corrosion kinetics. So here we are talking about rebar corrosion and not of the resistivity of concrete. So these two are eliminated. And only in the Nernst equation we looked at when we are discussing about the corrosion potential, and it is used for determining the equilibrium potential. So that's where we use this equation. So therefore the right option is A, it is the equilibrium potential. Okay, question 17. So we are given with three statements and we have to say pick which of these are true. So the first statement is that pitting corrosion leads to loss of mass in rebar. Statement 2 is the use of blended cements reduces protection against corrosion in RCC. And statement 3 is the epoxy coated bar helps to improve the protection against corrosion in the rebar. So the options are 1 and 2 are true, 2 and 3, 1 and 3 and 2. Okay, we have one vote for option C, both 1 and 3. Any other answers? Okay, one for B, 2 and 3. Alright. Any other answers? Alright, so let's take a look at the right options. Right option is C. It is both the statements 1 and 3 are true, not the statement 2. Okay, so one statement 1 and statement 3 are correct, true statements. Okay, so why is that? So statement 1 says pitting corrosion leads to loss of mass in rebar, right? So we looked at the effects of corrosion, right? So in that, one type of corrosion is the pitting corrosion that was discussed. So what happens in the pitting corrosion? So it is basically it happens when you have corrosion occurring from external as an external attack, right? So because of this, you will have what you will have is a localized attack on your rebar. So suppose you have your rebar like this, and because of the external intrusion, so when you have corrosion occurring, so it will be taking place in a localized region in your river. So what happens that is after this corrosion takes place, what you'll have, you'll end up with something like this, right? So this is the pitting corrosion. So you can see that the attack has corroded the rebar in a particular region. So that will lead to actually your loss of rebar. So the material that was present in this region, it is now corroded, and because of that, you will have a loss of mass that is happening. Right? So therefore, pitting corrosion is leading to this loss of mass. So that is a correct statement. Statement 2 says that the use of blended cement reduces protection against the corrosion and RCC. So this is incorrect. Why? Because blended cement actually improves your protection, right, against corrosion. So we already saw this, one of the strategies that we could adopt to protect against corrosion. So to protect or to delay, the corrosion, right? So it was to use blended cement. Why? Because blended cement offers you, better protection against intrusion, because the porosity is controlled, right? So it will be actually reducing when you're using blended cement, because you'll have because the porosity is reduced, and therefore it will offer greater protection and not reduced protection, right? So therefore the given statement is opposite to what actually happens when we use blended cement. Therefore it is incorrect. 2 is incorrect. 3 is epoxy coated bar helps to improve the protection against corrosion. So again, this we already discussed. One of the strategies is to help is to have a better proofing, right? So having a coating that helps you prevent this intrusion of moisture and oxygen. So that will help you with your help you prevent corrosion. Therefore, given statement in 3 is true. So out of the three, statements 1 and 3 are correct, 2 is incorrect. So the right option is C, 1 and 3. Okay, question number 18 is, which of the following governs the ingress of fluids in concrete? So the options are porosity, pore size, pore shape, and all the above. vote for option D. Yeah, we'll take a look at the answer. We can choose one for now. We'll see the answer. Okay, any other answer? Okay, so I'll take a look at the answer. The right option is option D. It is all the above, right? So we are talking about ingress of fluid. So the porosity, it is the volume. So the size also matters, and the shape of the pores also it will determine the connectivity of the pores, right? So when you have better or interconnected pores, you will have higher permeability as we talked about, and also higher volume of pores, and also the size of the pores. All these three have a role to play on what is the or how much there will be ingress, right, in the of the fluids in the concrete. So all of these three affects here uh, the degradation process, right? So they all three contribute to the fluid ingress. So the right option is D. It is all of the above. Okay, question number 19 is, which of the following is not a characteristic of the high strength concrete? So the options are high porosity, low water to cement ratio, presence of pozzolanic material, and use of high range water reducing agent. We already have one answer as option A. Okay, we have two answers for A. Okay, any other answers? Okay, let's take a look at the right answer. So the right answer is option A. It is high porosity. Right. So here again we are talking about high strength concrete, and the question is which of the following is not a characteristic, right? So which of this is not seen in high strength concrete? So so we see that for high strength concrete. So we already talked about what is the role of porosity. So when you have higher porosity, you will have lesser strength, right? So when the concrete is weaker because the porous regions is not contributing your strength. So when you have high porosity, your strength reduces, right? So because we want high strength concrete, we cannot afford to have high porosity. So this is actually the right option. So lower water to cement ratio, again, we discussed this. So water to cement ratio plays a role, and lower the water to cement ratio, you'll have better strength, because water to cement ratio actually has an effect on porosity, right? So initially, the relationship that was developed between the strength was with the water to cement ratio, but later it was shown that water to cement ratio has a role to play on porosity, right? So when you have lower water to cement ratio, you'll have lower porosity as well. So your strength will improve. So this is seen. So this is a characteristic. And the presence of pozzolanic material, again, it has a role to play with reducing the porosity, because of these are finer materials, and also the pozzolanic material have some cementitious property. They help in developing additional bonds. So that will also help in increasing the strength. And the third is the use of high range water reducing agents. So this is also seen or used for high strength concrete. So again, we discussed it previously, because we are working with a lower water to cement ratio, your workability will come down, right? So but we need higher workability, for the ease of placing and mixing. So we cannot increase the water content to increase the workability, because that will affect our strength. So we go for the using high range water reducing agent. So all the three options B, C, D are actually a characteristic. So it is only A which is not a characteristic of the high strength concrete. So the right option is A. Okay, question number 20 is the strength of different phases such as ITZ, the cement paste and the aggregate becomes almost equal in high strength concrete. Is the above statement true or false? Give me a one more for A. Okay, any other answers? Okay, so let's take a look at the answer. So the right answer is option A. The given statement is true. So what is the statement saying? So the strength of the different phases such as ITC, cement paste and aggregate becomes almost equal in the high strength concrete, right? So I mentioned about the different phases, right? So that we looked in the previous weeks, right? So it was the three phases that we see are the interfacial transition zone, the cement paste and the aggregate. So these are the three phases that are present in the concrete, right? So so we looked at in the ordinary concrete case. So it is the failure that failure happens, or the cracks propagate through this ITC, right? So that's what we had seen, because this is the weaker of the three phases, and therefore the weakest version is what that will fail, and therefore the cracks will propagate through this. So that's what we saw in the case of the no ordinary concrete, right? So or the normal strength concrete. So if you look at it, so aggregate will have the higher strength. The higher modulus will be seen for aggregates, and then for for cement base will be somewhere like lower, and then for concrete. So because it is a mix of the both aggregate as well as the cement, so the concrete will have somewhere in between. So in the normal case, whereas in the high strength case, what we do, so we are not strengthening the aggregate, right? So we are using the same kind of aggregates. So aggregate is will have the same strength still, but what we are doing is we are increasing the cement base strength, right? So we are using increasing the strength of the cement. So what will happen is they will become closer to the aggregate strength, and therefore your concrete strength will also improve, right? So that's what we are doing in the high strength concrete. So what we see is that the strength is becoming almost similar between the different phases than we see in the ordinary case, right? So therefore, the failure will happen not just in the ITC, but it will also pass through the aggregates as well in the high strength concrete. So because they are having equals, almost equal strength in this case, therefore the given statement is true. Okay, question 21. So we have four statements. So we have to pick which of these are true. The first statement is the continuous grading of aggregate is required to ensure high packing density. Statement 2 is effect of stress concentration at the ITC in fine aggregates is lower than coarse aggregates. Statement 3 is high strength concrete fail at higher levels of stress and strain as compared to conventional concrete. And statement 4 is high strength concrete offers higher resistance due to low porosity and low pore size. So which of these are true? The options are 1 and 4, 2 and 4, 1 and 2, and 2 and 3. We have one answer as A. Okay, any other answers? Okay, one more vote for option C. Okay, let's take a look at the answer. So the right option is option C. Statements 1 and 2 are correct. Okay, only 1 and 2, not 3 and 4. Okay, so what is given in statement 1? It says that a continuous grading of aggregate is required to ensure high packing density. So this is a correct statement. So we have looked at this before in the earlier lectures itself, how gradation affects your packing density. So when you have a mixture of different sizes, so that will generally improve your packing density, because so when you have a higher size particle, so they'll give you some packing, right? So depending on their shape, but there will still be some voids left by those higher size particles. So when you have a next smaller size, so what it will have, it will ensure that it fills the voids created by the higher size. But and there will be some voids created by the smaller size particles as well, which can be filled by even smaller size particles. So when you have continuous grading, so what you are making sure is that, so every size, the voids created by a one size is filled by the void is filled by the next lower size, right? So by doing so, what we are doing is we are reducing the voids in our system, and therefore will achieve a higher packing density. And so therefore, continuous grading will help in achieving higher packing density. So that statement is true. So second statement is the effect of the stress concentration at the ITC in fine aggregates is lower than the coarse aggregates. So this is also a true statement, because so we saw this before. So when we are going for high strength concrete, so we prefer a lower MSA than a higher MSA. So lower MSA means more finer aggregates than higher MSA is for coarser aggregates. So we saw that there will be stress concentration developing around the the aggregates, right? So when you have coarser aggregates, what happens is the stress concentration will be over a larger area, larger region, because their size is larger. So therefore, the stress will be higher around coarser aggregates, or it will be higher around coarser aggregates compared to finer aggregates, right? So the given statement is true. It is saying that around fine aggregates in its ITC, the concentration will be lower because its MSA is smaller than coarse aggregates. So that is correct. Statement 3 says high strength concrete fail at a higher stress, higher levels of stress and strain as compared to conventional concrete. So this is incorrect, because even though high strength concrete can take more load, so they can resist higher stresses, but they need not or do not produce higher strains in comparison to your conventional concrete, because we are again not talking about the role of the reinforcements, right? So it is still the concrete as such, only the strength is increased, right? So it can take more compression now, but still when failing, it does not produce higher strain. It's not going to give you higher or better warning than your conventional concrete for failure. So it can still take higher levels of stress, but it will not give you a higher strain than your conventional concrete, right? So therefore, one part partially it is true, but not it is completely true. So statement 3 is incorrect. Statement 4 is high strength concrete offers higher fire resistance due to its low porosity and pore size. So this is also incorrect. While high strength concrete compared to your conventional concrete offers improved performance on different factors, fire resistance is not one of those properties which we see an improvement in the high strength concrete, right? So therefore, statement 4 is also incorrect. So out of the four, only statements 1 and 2 are correct, which is given in option C. Question 22. So statement, again the four statements are given. So the first one is paste content is higher in the self-compacting concrete to make it more workable. Statement 2 is drying shrinkage is higher while autogenous shrinkage is lower in high strength concrete as compared to conventional concrete. Statement 3 is macro defect free cement ensures application of high pressure onto paste to increase the strength. And statement 4 is high strength concrete has low abrasion resistance, hence its application is in flooring. Okay, which of the statements are true? So the options are 1, 2, 1, 3, 1, 4, and 2, 4. We have one vote for option A. Okay, any other answers? Okay, so we have one option for option B. Okay. Okay, let's take a look at the answer. The right option is option B, statements 1 and 3. Okay, so only 1 and 3 are true, 2 and 4 are incorrect. Okay, so statement 1 says that the paste content is higher in the self-compacting concrete to make it more workable. So this is true. So self-compacting concrete, so we discussed this. So then the self-compacting concrete, we want, to so it needs to be more flowable, right? So therefore we eliminate the need for compaction, right? So external compaction. So therefore it has to be more workable. But for that we need a higher paste content. Right. So when you compare the aggregate content to the paste content, so aggregates are not as flowable as here paste. So when you want more workability, so you'll have to have a higher paste content. So therefore you'll have more flowability. So therefore statement 1 is true. Statement 2 is that drying shrinkage is higher while autogenous shrinkage is lower in high strength concrete as compared to a conventional concrete. So this is incorrect, right? So we looked at different types of shrinkages in, I think, the 2 modules ago, right? So when we were discussing about shrinkage, so in that, so your drying shrinkage is because when you have excess, moisture, whereas autogenous shrinkage is because of the self-desiccation, right? So because of the hydration process itself, you will have a reduction in your volume. So that's the autogenous shrinkage. So when we are talking about high strength concrete, there will be higher or more hydration, right? So compared to your conventional concretes, right? So therefore, the shrinkage that we see will be more of the autogenous type in the high strength concrete because of this higher rate of or higher hydration that is occurring in the high strength concrete, right? So therefore, um, this component will be more in comparison to the drying shrinkage. The drying shrinkage is also lower because of your in high strength concrete we are using a lower water to cement ratio, right? So there is not excess water that is getting lost, which is the component that plays a role in the drying shrinkage, right? So that because of the low water to cement ratio also you will not see drying shrinkage more in the high strength concrete. Right? So the given statement is wrong because it says the opposite, that drying shrinkage is higher than autogenous shrinkage, right? So it is the other way around. So therefore statement 2 is incorrect. Statement 3 is that macro defect free cement ensures application of high pressure onto the base to increase the strength. So this is true. So again, in the one of the special uh, concretes that we looked at was using use because of the use of the high pressure and also the treatment with temperatures to get this macro defect free cement, so for high strength applications, right? So this was one of the methods that we looked into. I mean, this is not applicable or not, produce. We cannot produce it in the field directly because it requires, production in a factory environment. But it's still we can produce high strength paste by the use of high pressure. So therefore, statement 3 is also correct. Statement 4 is that high strength concrete has low abrasion resistance, hence its application in flooring. So this is incorrect. So actually, it has high abrasion resistance, right? So we looked at one of the applications. So we looked at DST. right? So, and we discussed that it has a higher abrasion resistance, which makes it possible to use it for flooring applications, right? So, because we want higher resistance to abrasion. So, but here the statement is giving the opposite, result. So it is actually higher, not lower. And because it has a higher resistance to abrasion, that's why it's used in flooring. So the reasoning given is incorrect. So statement 4 is wrong. So out of the 4, only statements 1 and 3 are correct. So which is given in option B. So the right option is B. Okay, so question number 23 is the parameter which captures the effects of porosity and the pore characteristics on permeability is called dash. The options are crack density, tortuosity, reverberation, and parching. Any answers? Okay, we have one vote for option A. Any other answer? Okay, let's take a look at the answer now. So the right answer is option B. It is tortuosity. Right here we are talking about the effect of porosity and pore characteristics. So the parameter which captures these two. So if you remember the model for permeability that was discussed, right? So it had different parameters. So one of the parameters, if you remember it, it was tau. So which was called tortuosity, right? So this is actually the parameter that captures the porosity and pore characteristic effect. So what it is basically, so when you have 2 points between which flow is taking place, so in your system flow will not always take place directly, right? So because it depends on how the pores are interconnected, so the flow will take place on some curved path, right? So it is the length of this path in which the flow is taking place to the length of the straight line path that connects the 2 points between which the flow is occurring. So that ratio is generally how tortuosity is defined, right? So, and this will depend upon your pore structures, right? So how much, what is the porosity as well as the interconnectedness. So that is what characterizes this flow path. So that is captured by this factor tortuosity, right? So therefore that is the factor that we use in our permeability estimations, right? So to capture this characteristic. So the right option is B, it is tortuosity. So crack density, it's not related to your permeability, and corrosion is also not related. Arging is generally, it's for a smooth finish. So when you want to have a smooth finish, so you create a surface with mortar, right? So a cement base. Right? So that is what we generally call as parging, right? So this is also not related to your permeability. So it's only the tortuosity which is the parameter that captures this. Okay, so the right option is B. Okay, any questions? Okay, so there are no questions. So we'll wind up the session here. So this was the last question for this week. Okay, so if you have any questions or clarifications you need, you can ask. Otherwise, we can close the session here and meet again next week. Thank you. Okay, so if there are no questions, so we'll stop the session here. So we'll meet again next week. Okay, thank you for attending.